Okay, hey, this is Ashton here for my submittal of Lab 7 for embedded systems here at the University of Memphis. So for this lab, we had to design a finite state machine using Vhdl or Verilog or system Verilog to put on an FPGA. And what this VSM is supposed to, or this FSM, what this FSM is supposed to do is check if an input binary sequence is equal to 11010. So the way I designed this FSM is we've got two states, an idle state and a compare state. Whenever the FSM is reset, it goes right to idle and sets output to 0. If reset is 1, then we check enable. If enable is 1, then we actually do the comparison. If enable is not equal to 1 or if it's equal to 0, we just stay in idle. So when reset is 1, enable is 1, that's when the device is fully enabled. It does a comparison operation. If we are equal to the sequence 11010, then our output is 1. If we are not equal to 11010, then our output is 0. And no matter what the result of that comparison operation is, we just go right back to S-idle. So as far as an FSM, this is really pretty simple. And the reason being is if we were to just think about the circuitry behind this, really all we've got is a clocked comparator. We've got a comparator that compares this D-in, our input, whatever it may be, to 11010, and it just maps that output into a D flip-flop. And just every clock cycle, we update the flip-flop. So that's so that kind of explains why I've only done two states here for my FSM. It's because what am I really doing? Well, I'm either comparing or I'm not. And if I'm not, it's because either my reset is low, because it's an active low reset, or my enable is low, active high enable, disabling the device. So yeah, that's why this FSM is so simple. Let's look at the VHDL and the waveforms, and let's talk about how I implemented this. So over here, I've got Vhdl open. You can see my VHDL. I've just got 4 inputs. I've got a clock, a reset, and enable, and then my data in, and then I'm outputting my comparison value. So like, is it equal or is it not? Since I'm defining an FSM in VHDL, I'm declaring a state type data type with 2 possible values, idle or compare. Then I'm declaring a FSM state signal that starts off at S-idle, and it's a state type data type. And here's the actual implementation of my FSM here. So we're sensitive to the clock and reset. A reset is an active low asynchronous signal. So whenever reset goes low, I'm going to set my output to 0 and go right back to idle, and then just stay there as long as reset is low. But if reset is 1, then on the rising edge of my clock, I'm going to go into my FSM implementation, go to idle, or my comparison is set to 0, I'm going to check enable. If enable is high, then I'll move from idle to compare. If enable is low, then I just stay in idle. But if enable is high, let's go compare. So essentially we grab the result from a comparator, map that to our output of comparison, and go back to idle. If my state isn't idle or compare for whatever reason, so that's when we enter this when others block, then set the output to 0 and go back to idle. So that is how I've decided to implement this FSM. As far as my test bench, here let's see here. So I import my component for testing. I've declared my test signals, my clock parameters. I've instantiated my component, created my clock signal, and then here's my stimulus process. So I start off by just setting all of my inputs to 0, giving it a few clock cycles. That's 3 clock cycles there, and just see what happens. And then I actually enable the device and start bouncing between inputs and see what happens. So you can see I set my input to 11010, wait 3 clock cycles, then set it to all 1s, wait 3 clock cycles, then set it back to 11010, wait 3 clock cycles, and then wait for eternity. That's what this test bench does. And let's look at the waveform. So, looking at the waveform here, we've got some interesting results. Some things may look confusing, but I promise I can walk you through all of it. So, here's where all the inputs are 0. Notice our output is 0 and we're in idle, just as intended. We set reset and enable high, so the device should be enabled. Now it should be working. 1 clock cycle later, we're actually going to go to compare. And then 1 clock cycle after that is when our output goes high in what seems to be the S-idle state. So let's talk about this for a second. First, why does it take 2 clock cycles to go high? First, whenever you set, notice here what I'm doing is I'm enabling the device right on a clock edge. Whenever you do that in the Vhdl simulator, it makes this assumption that those enable signals, if they go high exactly on the rising edge of a clock cycle, they're actually not going to arrive to the device until right after the clock cycle ends. So even though it looks like my control signals have gone high right on the clock edge, and I should move to compare the next clock edge, the simulator looks at this and says, no, those signals, because of practical limitations of digital circuits, because of delays, those come in after the rising clock edge. So it's actually not until here that the FSM actually recognizes that, like, hey, I'm enabled, and that's why compare goes high there instead of here. It's because this is when the FSM recognizes, hey, my enable signals are high, let's get to work. So that's why the compare, the switch to the compare state is a little bit delayed. Next, what we have is, why is the output high when it's in the idle state rather than in the compare state? And the reason for that is because I used a one process FSM and some timing. So in my FSM, I did a one process finite state machine. And so you'll notice that whenever enable and reset are high, inside idle, we set the state to compare. So what's happening is right here, we're in the idle state. The next state is compare. And that's when we went high, just as we were supposed to. So because I haven't built an FSM that uses a current state, next state kind of functionality, it's just whatever my current state is, every output is really, every output is really associated with the state before it. That's how this is working. So that's why my output goes high during idle instead of compare, and that's why my compare is delayed by 1 clock cycle. I hope this timing is starting to make sense now. But now also notice when my input is not that matching sequence, it just stays 0. It's doing good. And then I set my input to 11010 for all time. You'll notice I alternate now. It takes 2 clock cycles after being enabled for it to recognize that it has the proper input. But then after that, it's only going to take 1 clock cycle. But because my idle state sets output to 0 and my compare state sets output to 1, I'm going to toggle back and forth between 1 and 0 and create this 50% duty cycle PWM as my output. So what I'm going to do here is I'm going to, so if I were putting this onto my FPGA, what I would probably do is map my output actually to an LED, so that 50% PWM just looks like a dim green light instead of seeing like 1, 0 flash on and off really rapidly. I would just map this to an LED so that it's just a LED controlled by PWM, and I can very clearly see just when the LED is on, that's when it's getting the PWM, that's when I have the right input, and when it's off, it's when I don't have the right input, and in other words, I have a 0% duty cycle. So yeah. So since my final project for embedded systems is an FPGA project, I have to actually show this working on the board. I've got to make a couple edits real quick to get this to the board in a way that I can use it, because I don't have an infinite number of slide switches on my board. So I'm going to adjust this FPGA module a little bit so that it takes in just a 3-bit input instead of a 5-bit input. And then I will hop back into the video and I'll show you what all I did. Okay, so now for part 2 here, I'm going to show you it working on the FPGA. So, the changes that I had to make here. One, I only have 2 slide switches I can really use for data in this FPGA, or in this design. Since I've only got 4 slide switches and 2 of them are going to be used for controls, my reset and enable. So as you can see in my XDC file here, I'm going to use my 12 megahertz clock. That's one that they typically prefer you use for logic on this board. I'm using all of my slide switches. The right two are for my data in, the left two are for reset and enable, and then I'm going to show the output of comparison on an LED. So I've already synthesized this, generated a bit stream, all that. I've gotten it onto my board and I'm going to show it to you working. So get a better view of the board here. So here's my board. Reset and enable are low right now, so it's not going to do anything. Set reset high, still not going to do anything because we're not enabled. But reset and enable are high. I've got it right now so it'll recognize the sequence 1, 0. So right now I've got in 0, 0, not going to do anything. 0, 1, not going to do anything. 1, 0, we see that LED 2 has gone high. But 1, 1, and it goes back low. So we are correctly detecting 1, 0 on our LED. So yeah, there we go. We've got this FSM fully written in VHDL, simulated, and working on the board. Thanks.